light from the invisible. Look up, and the night dresses itself in color. Curtains of green and purple that dance above polar skies. Those auroras, our planet's most luminous weather, are the visible signatures of invisible forces, charged particles, magnetic fields, and atmospheric gases locked in an electromagnetic ballet. But Earth is not unique. Across the solar system, planets more massive and more exotic than ours host auroras that dwarf anything we've seen here. Sheets of ultraviolet light on Jupiter, X-ray flashes in polar hotspots, and faint infrared glows on the distant ice giants. These lights are more than spectacle. They are diagnostics, windows into the invisible architecture of planetary magnetospheres. Tonight, on Beyond Earth, we follow those lights, how they form, how they differ on giants like Jupiter and Saturn, and what they reveal about the magnetic hearts of worlds. How auroras form, the physics of light and field. At their core, auroras are simple, energetic charged particles, electrons and ions, collide with atoms and molecules in a planet's upper atmosphere. In that collision, the atmospheric particle is excited. When it relaxes to a lower energy state, it emits a photon, a packet of light. The color, intensity, and altitude of that light depend on the species involved: oxygen, nitrogen, and hydrogen. Energy of the precipitating particles and the atmospheric composition and density where the collisions occur. On Earth, for example, oxygen produces the classic green at 557.7 nanometers, while nitrogen produces purples and reds. The charged particles arrive along magnetic field lines and deposit energy primarily at high latitudes because magnetic field geometry funnels them toward the poles. That simple picture, particles, field lines, and atmospheric emitters, underpins auroras from Mercury to Neptune, but the details change wildly with planetary environment. Two physical processes supply the particles. First, the solar wind, a stream of charged particles flowing from the sun, can connect with a planet's magnetic field, inject energetic particles, and cause day-side reconnection that funnels plasma toward the poles. Second, for giant planets, a powerful internal engine can dominate. Rapid planetary rotation, strong magnetic fields, and contributions from volcanic moons, ionospheres create currents and plasma populations internal to the magnetosphere itself. It is this interplay between external forcing, solar wind, and internal dynamics, rotation, moon-driven plasma, that makes planetary auroras so richly diverse. Jupiter, the king of auroras. No world flaunts auroras like Jupiter. Jupiter's auroral ovals are permanent, brilliant, and complex, visible in ultraviolet, infrared, radio, and even X-rays. Several processes sculpt these lights. A steady main oval tied to magnetosphere-ionosphere, coupling and rotational dynamics, polar emissions and transient bright spots driven by magnetospheric dynamics and interchange injections. The famous moon footprint, a bright spot linked to the interaction of Io, and to a lesser extent, Europa and Ganymede, with Jupiter's magnetic field, generating a current system that prints a luminous trail on the planet's atmosphere. Spacecraft and telescopes have revolutionized our view. The Juno mission has mapped auroral electrons, electric currents, and the energy distribution feeding Jupiter's lights, and Earth-orbiting telescopes such as Hubble have tracked the ultraviolet morphology with unprecedented detail. Recent observations show extremely rapid variability, auroral brightenings on sub-second to second timescales in certain bands, and infrared measurements reveal powerful H3+ emissions that trace the auroral energy budget and thermospheric heating. Jupiter's auroras are powered by internal plasma processes driven by rapid rotation and moon-fed plasma, a system in which rotation, moons, and magnetosphere conspire to produce auroral power, far exceeding that supplied by the solar wind alone. Saturn, rings, ice, and electric lights. Saturn's auroras are cousins of Jupiter's, but shaped by different rules. Saturn's magnetic field is weaker than Jupiter's, and the planet rotates more slowly. But Saturn hosts powerful auroral displays tied to both solar wind forcing and internal plasma sources. Notably, Enceladus, whose water-rich plume feeds the magnetosphere with fresh ions. Cassini's in situ measurements and ultraviolet imaging showed that Saturn's auroral power varies with solar wind pressure, but also correlates with Saturn kilometric radiation, SKR, and magnetospheric current systems. Near the poles, Cassini observed the auroras in ultraviolet and visible light, and late in its mission, made low-altitude passes that refined our picture of how currents close through the ionosphere. Recent analyses even point to wind-driven auroral features near the pole where atmospheric dynamics shape the magnetic mapping, a phenomenon that offered new clues to the planet's rotation and internal processes. Saturn's auroras are therefore a hybrid, solar wind-modulated, moon-fed, and atmospherically sculpted. Auroras on Uranus and Neptune. Out past the gas giants, the auroral story becomes stranger. Uranus and Neptune have magnetic fields tilted and offset relative to their rotation axes. Their magnetospheres are warped and asymmetric. That geometry produces auroras that are patchy, variable, and sometimes located far from the poles. Neptune surprised observers when the James Webb Space Telescope and other facilities produced infrared and UV detections of auroral activity at mid-latitudes and polar regions, revealing that even the distant ice giants host complex magnetosphere-atmosphere coupling. Recent JWST work found auroral emissions in unexpected places and raised new questions about how magnetospheric structure and seasonal atmospheric changes influence auroral production at Neptune. Auroras are not mere beauty. They are a language written in photons and fields. If you want more luminous mysteries unpacked, subscribe to Discovering the Unknown. We'll chase the next auroral flash to the farthest planet.